Good morning, dear students. Welcome to another session of Verilog HDL. So in the previous session, we discussed regarding gate level modeling and how do we instantiate the logic gates and how do we make, and we took up an example of 4 is to 1 mux and 1 bit full adder. How we implement those using the Verilog code at the gate level of modeling. So that is this example we had seen. Okay. So again, just a recap of these things. So what you should be doing is you should know what you have to implement first. Then you should write down the truth table for that. So based on the truth table, obtain an expression for the circuit what you want to implement. So based on those things, you can write down the Verilog code. So the example is they have taken 4 is to 1 mux. So they want to implement this. So based on the select lines, one of these lines will be selected and presented at the output. So that is what this truth table is specifying. So based on this, if I take an example, if S1 is 0 and S0 is 0, then I naught has to be selected. How I can go ahead with this? So what they have done is they have taken a AND gate. So to one input they have given I naught, and to another input they have taken the result of S1 and S0, S1 and S0, but both have to be 0 in order for the output to be equal to I naught. That is whatever is present at the input. So for, so for this purpose, what they do is they have placed inverter before the S1 and S0 parameters. That is, they have placed an inverter here, and to this they have given S1 and S0. Now, if S1 is given to the inverter and this if it is 0, what happens is the result will be 1 here. So 1 will be appearing, and even if S0 is 0, after inversion it will be 1 here. So 1 1, and whatever is the value of I naught will be present at the output of the AND gate. So that is how it is working around here. That is how they are working. So why not? So that is given to the OR gate. So if any one of these inputs is 1, the output will be 1. So in general, when you just observe, what happens is based on which data is selected, that data will be appearing at the output. So that is how this circuit diagram is represented. So remember, first see what you want to implement, then write down the truth table. From truth table, if you can obtain the a logic diagram, you can obtain the logic diagram directly, or you can simplify the equation, that is use K-map or QM method in order to identify the literals and other stuff and try to implement it. So once that is done, how you rig up the circuit in the breadboard, right? In the same fashion, you have to write the code. So in order to do that, you should first draw the logic diagram of your implementation. So from the logic diagram, I should try to identify which are the intermittent signals which are required. So intermittent parameters or signals, whatever you can just specify. So these are your regular parameters in this case, and this is one regular parameter. The others are like your wire connections. So you have to connect these using the wires to the AND gate. So output of this one using the wire to the AND gate. So it is like this fashion. So that is how this code is written. So similarly, we saw 1 bit, and if I want to see how this implementation is working, then I have to go for stimulus block. So in which you'll be providing the input to the implementation what you have done to this implementation, and you try to see what is the overall result. So we were discussing regarding this. So first, say in this case, what we have, I wanted to implement say 1-bit full adder. So you should know what is the truth table: A, B, C in, sum and C out. So you should write down all the combination and see what is the sum and C out for all these conditions. So based on this one, you get the expression as sum will be equated to XORing of all these three, and carry will be obtained with this expression. So this is from the truth table after you have simplified it. So once I get this expression, now I have to implement it, or I represent it in the logic diagram form. So this is how you represent it. That is, this same expression is being represented here. So once you have done, so A and B, C in are the inputs, sum and C out are the outputs. So now I should, once I draw this logic diagram, right, I try to identify which are the intermittent parameters or signals which I have to establish. That is, which wire or which wire should be connected between the gates. So for example, this XOR gate is connected to the output of this XOR gate is connected to input of this XOR gate. And even the same thing comes to this one. So these are the things which are present in this case. Okay. So in this one, we'll be implementing the code for 1-bit full adder. So how these are internally connected. So if you just observe, A and B are given to this XOR gate, and output of this XOR gate is given as one of the input to the next XOR gate, whose result will be the overall sum. So here I should make use of the XOR gates. So if you just observe what we have, XOR gate, that is the first one. Input is A and B, and output is the XOR operation of the first gate, that is S1. So that is this parameter. XOR gate, input is A and B, and output is S1. Now this S1 is given as input to this one, and Cin is given as another input to this one in order to result out the sum. So here if I just check out for the sum, so next XOR gate, sum, this is the output. What is the input? Output of this XOR gate. Output of this XOR gate. That is, it is S1, and input are S1 and C1. So this is the overall result for the sum. And here you can see that there is no name identifier given to these instantiations. So this is permitted. So it is just basically to provide the connections. You are establishing the connections and you are obtaining the result. So similarly for Cin, you have AND gate, that is this one, this part. So one input is S1, the other input is Cin, and output is S2. So here we can see that AND gate, output is what? C2. Two of the inputs are S1 and Cin. And lastly, so yesterday I specified, this is actually OR gate. So it is just a printing mistake what they have done. So here input is what? C1 and S2, and output is C out. So OR gate, output is C out, C1 and C2 are the inputs. So this is your module definition, what you have provided. And this is a logical implementation. And since all you are using gates, right, this is gate level modeling. So again, what you do is if you want to stimulate this one, go for stimulus block and provide the appropriate inputs and try to see what execution will result in. So now the same concept, what we do is we can extend it to 4-bit triple carry adder. So here it is nothing but you can construct it from 1-bit full adders. We can construct it using this thing. So 1-bit full adder we have done. So we can have 4 such kind of definitions, or I can use a single definition and try to see how I can go ahead. So we'll just see what what is the implementation we have taken up. So here we can see that This is just the overall diagram. That is for 4-bit full adder. You'll be having C in and 4 bits each for A and B. 4 bits each for A and B, and sum also will be resulting in 4 bits. And if carry is there, carry C out will be generated. So this is the overall general block diagram. Now let us see, and the implementation of adder. So this is like 1-bit full adder. This is 1-bit full adder. This is also 1-bit full adder. So all these are 1-bit full adder, which will help us to obtain the 4-bit full adder. So now let us see what all things are present in the code now. Now again, I will be using this logic itself, because we know that in 1-bit full adder, sum is what? XORing of all these operations. So in each of this is how it will be appearing. And C out is given by this expression. So here if we just observe what we have defined a module by the name a module full add 4. So it is 4-bit full adder. And what is the input to that? What is the output? Sum and C out are the two outputs, and inputs are A, B, and C in. So this is the port list. Now I have to define I have to declare the ports. Now here, as we are specifying, we can see that is 4 bits each. That is 0, 1, 2, and 3. So we should be declaring it as vectors. So here you can see that output sum is of 4 bits. How do I declare a vector? I declare it in this form. This is how I declare it. And C out is what? It is just 1 bit. So just specify output C out. So by default it is 1 bit. So this is like vector, and this is the scalar. And inputs are also 4 bits. So this is how I define it. And input C in, it is 1 bit. So this is how we go ahead. Okay. I cannot put this here itself. What this will do is it will make C in also 4 bits. So I have to declare it separately. Even for C out also I have to do it separately. So now we have to go ahead with the internal nets or the wire connections, what will be present. So we have declared it as wire C1, C2, and C3. So it is, we can just see here C1, C2, C3. So what is happening is output of full adder, that is FA0, its output is consisting of sum of 0 and C1. Sum of 0 and C1. So how these are generated? These are generated in this form. It is like sum of 0 and C1 for the first one, FA0. Then for the second bit for this one, FA1, output is sum of 1 and C2. That is again in the same form. This is sum of 1 and this is C2. So internally you can see that this is how it is connected. So now what we are doing is we have full add. So what is full add? Full add is 1-bit adder what you have implemented here. This is the 1-bit adder what you have implemented here. So for this one, what should be the input? The sum parameter, C out parameter, A, B, and C in. So these all are what? These all are 1-bit. So you should remember this. These all are 1-bit in it's this thing, because this is 1-bit full adder. Using this, we are implementing the 4-bit full adder. So here what we have, full add. So we are creating instances of full add, that is 1-bit full adder. Say F0, FA0, FA1, FA2, and FA3. So these are the 4 instances what I have created. So it is FA0, FA1, FA2, FA3. So what should be the input to each? So here you can see sum of 0 is the output, C1 is the output, and input is A of 0, B of 0 and C in. So for the first one, if we just check what we have, sum of 0, C1, A of 0, B of 0 and C in. So similarly for others also we have in the same form. So sum of 1, that is the first bit, and here we can see. So here only one change what we have to observe is this part, that is C1, C1. So here you can see FA1, uh, it will be giving me output what? Sum of the first bit, carry of, it will be taking input C1, A of 1 and B1, and output will be C0 and sum of 1. So here what is happening? So that we are passing. So we are implementing 4-bit full adder using 1-bit full adder. So this is 1-bit full adder what we have. Okay. So using that we are implementing the entire stuff. So each full adder will be dealt with this part. This is how the implementation will be done. Okay. So based on this circuit diagram. So now I have to go ahead with the stimulation. Okay. So again, I define module stimulus. There is no port list for this one. So there is no port declaration which is required in this case. Now, what are the variables I'll be passing on in order to stimulate this 4-bit full adder? So I require two vectors, A and B, which will be acting as the input. So we have declared it as register data type, and another one C in. So these are your regular parameters, that is C in, these 4 bits. Okay. And so these are the parameters what you are giving as inputs. So that is these things. Okay. So those you have declared, and intermediately what you will be getting is you will be getting the sum, which is a vector, and you will be getting C out, which is a scalar because it is just 1 bit. Now how do I create? How do I go ahead with this one? So first I have to create an instance of the full adder, 4-bit full adder. So I have to create instance of this one, 4-bit full adder. So that is what full add 4 is provided, and FA1 underscore 4 is the name of this instance. So what are the parameters you have to pass? So you can just see it is sum, C out, A, B, and C in. So that is sum, C out. So that is from here, sum, C out. Then we have A, B, and C in. These are the inputs. These are the outputs. So once you have passed, so instance will be created. Now we have to pass on we have to see if we change these values, whether I'll be getting the overall result or not. So in order to do that, what we do is in module stimulus itself, we start off with the initialization. That is, we begin with monitoring. So this is also a system task. So this is also a system task, which actually gives what? So this one, whenever there is any change in the variable, right, that time, that time it will be displaying the result. And this one time, right, it gives you the current time of that system, what you are stimulating. So here, here we have what is A, B, C. So these things you are displaying, and then you are displaying the C out and sum. So what are the changes you are displaying over here? Now, so here we have. So this will be a monitoring, and whenever there are changes, right, that will be displayed on the screen. That will be displayed on the simulation screen what we are having. So this is what display will be consisting of. So now, so I try to change the input and see what is the overall result I'll be having. So here we can see, we again begin. So A, what we are doing. So this is what it is, 4 bits in length. It is decimal in its format. And what is the decimal value? Decimal value is 0. So similarly, B also is defined in the same form. Cin, if you just see, it is 1 bit in length and it is binary. It is either 0 or 1. So in this case, it is 0. So Cin is 0, what they have specified. So after 5 units of time, after 5 time units, what you do is you change the value of A. So what is A? Again, it is 4 bits in length. It is decimal and it is decimal number 3. That is, it is 0011 in your binary. So it is decimal 3. And B also you have changed. So this is 4 bits in length. It is decimal value. Its decimal value is 4. So similarly, you try out with the other conditions. You try out with the other conditions. So after every 5 time units, what you're doing is you are making some changes in the input and we are trying to see what is the result. So in the last one, what you have done is you have changed Cin to bit 1. So it is 1 bit in length, it is binary, and the value is logic 1. So these are the values what you're providing as input to this full adder, to this full adder via this instance, via this instance. So when you provide these things, what is happening? So there you can just observe. So we have, we'll be displaying these all things. Okay. So A, B, C in, then C out and sum. So these are things what they'll be displaying, and it will be displayed in bits. Percent %B is specified as bits. It will not be displayed as your decimal number. So here at the 0th instance, that is 0 time unit, A is what? 0, B is 0, and C in is 0. So that is the first condition what we had given. So for this one, what should be C out? C out should be 0 and sum should be 0. So if the implementation is correct, you will be getting this result. So after 5 time units, A is 3, B is 4. So that is what is given. 5 time units, A is 3, B is 4, and C in we haven't changed, so it will be taking the previous value. We haven't changed, so it is 0, so it will be continuing with 0 itself. So when that is the case, if I add it, so you can just check out what is the result. 0011. So the result is actually 7. So 0111. So sum is 7. There is no carry. So C out is 0. So similarly, at this point, you can just check. This is 9. This is 9. So that is, I think, this is this one. Yeah, that is this one. And C in is 0 because it is taking from the previous this thing. So what is 9 plus 9? It is actually 18. Hmm? So when you sum it up, you can just check what will be the overall result. That is 1001, 1001. When I add it, it will be 0, 1, 0, 0, and 1. So here one carry is generated and this is the result 0010. So we can see that sum it is provided as 0010 and C out is 1. So similarly, if we continue, we can analyze the other conditions. Okay. So this is how it is implemented. So how 4-bit full adder is implemented. In order to implement 4-bit full adder, what we do is we first build bit, 1-bit full adder. So using these 1-bit full adder, what we do is we create 4 instances of this. So when we create 4 instances of this and using sync, right, I'll be getting the 4-bit full adder. So first implement 1-bit full adder. Using this module, you build the 4-bit full adder. So that is what you're trying to implement in this case. So next one, we have gate delays. Now you might have observed when you are rigging up the circuit, right? You give the input, but say you have connected a AND gate. Say you have given input A and B, and you are observing the output of this result. So what happens is you have changed the input. Say previously it was 0 0, now you made it 1 1. But what happens is after some amount of time, sometimes it is observable, sometimes not observable. After some amount of time, you will see the result is changed. So it is all because of the delays which are present in the circuits. So even this option has to be provided in a Verilog. So how do I go ahead with providing such kind of delays? Now in circuit diagram, you might have seen that so such kind of representations wherein you have something called as rise time, fall time. You have something specified in this form, right? Rise time and fall time. So here also we have all those things. So how do we specify those parameters in your circuit? No, sorry, in your Verilog code. In your hardware circuit, it is present because of your ICs and other steps what you are using. But in your simulation, right, how do I incorporate these things? Because it is hardware description language. So how the hardware behaves, in the same way I should provide this information. So for that purpose, we have gate delays which we can specify in Verilog. So we have three kinds of delays, that is rise, fall, and turn off delays. So what is meant by rise delay? So rise is nothing but you are moving to logic 1. You are moving to logic 1. So you might be moving to logic 1 from any of these conditions. Previous state might be 0, it might be X, or it might be Z. So from these states, the time taken to reach to logic 1 or time taken to reach the say logic high value. So that is the rise delay is associated with the gate output transition to 1 from another value. So it is the time taken by the gate to change its value from either of these 0, X or Z to logic 1. So then we have fall delay. Fall delay is related to transition to 0. That is output of the gate should go to logic 0. So previously it can be any state 1, X or Z. So it is a time taken for the gate to transit from any of these three states to 0. Any of these three states to 0. So the last one, what we have, turn off delay. So here, turn off delay is basically associated with the gate output transition to high impedance. High impedance. So here, so it is like you have connected the circuit. You have connected the circuit, and you have a wire over here. So if you remember on wire, when nothing is present, it is considered as it, and it doesn't hold any value. Remember, so it will be in high impedance state. So that is what turn-off delay specifies. Turn-off delay is associated with the gate output transition to the high impedance state. So previously it can be anything. So the time taken for that gate to reach high impedance will be termed as turn-off delay. Hmm. Okay, so there are different ways of specifying these delays. So remember again, rise delay is related to moving from any of the states to a logic high. The time taken to transit from any of the previous state to logic high. Fall delay is transition of the gate from any of its state to logic 0. Turn off delay is transition of the gate from any of its previous value to its high impedance state. Now here we have another thing, that is what if I specify only one delay what if I specify 2 delays and what if I specify 3 delays? So in order to come to this, we'll just check out how we specify it. So then I'll come to this parameter. So we have 3 different types of delays, that is rise, fall and turn off. So how do I specify these things in your gate level simulation or modeling? So for this purpose, what we do is, so and keyword, we specify hash and what is the delay time, hash and what is the delay time. So this is A1 is the instance of and these are the parameters of the ports what we are defining. So here you can see that there is only one delay time which has been specified. So example, we'll come to example of this one. So here we have and hash in brackets we have specified 5. So what does 5 imply? 5 implies it is 5 time units of delay and A1 and these are the parameters. So what this does is if I'm specifying only one parameter, if I'm specifying only one delay, so that is what this specifies. If there is only one value specified for the delay, then that delay will be applied to all the transitions. That is, whether it will be applied for rise delay, it will be applied for fall delay, and it will be applied for turn off delay. So it will be applied to all. Okay. So this is what only one delay, when if only one delay is specified, what happens. So next one, I'll be able to specify 2 delays. So in this one again, and hash in brackets you give the 2 values. So for example, here it is like rise and fall delay. So the 2 parameters we have specified separated by a comma and next to the instance and the parameters. Now the example of this one is you can see here. So here we have and hash 4 comma 6. So what is 4? 4 is related to the rise delay. 6 is related to the fall delay. So now here we can see that we have specified only 2 delays. We have specified only 2 delays and A2 and these are the ports. Now in such case, so previously what was there? Only one parameter was specified, only one delay. And same thing was applied to all 3, rise, fall and the turn off delay. Now here we have given rise delay and fall delay. But what should be the turn off delay? Turn off delay will be smallest of these 2. So in this case, turn off delay will be equal to 4. That is smallest of these 2. So that is how it will be considering. So here it is. Turn off delay will be minimum of the 2 delays what you have specified. Now we have other condition that wherein we'll be specifying all 3 delays. That is rise delay, fall delay, and the turn off delay. So all 3 values will be specifying. So here we have that example. So here we have. So how do I specify? So here we have just one buff if hash rise, fall, and turn off. So I have to write it in this sequence only. I cannot change it. I cannot specify. I can if I want a fall delay of 6 and rise delay of 4. I cannot write it as 6 comma 4. So 6 will be associated with rise and 4 will be associated with fall delay. So you should not be mixing it up. So it should be given in this sequence only. So we are having rise delay, fall delay, and turn off delay. All 3 will be specified within this bracket. And then your instance. So the example is buff if 0 they have given. So hash 3, 4, 5. So the first one is related to the rise delay, next one is related to the fall delay, and the last one is related to the turn off delay. So it is 3 time units. It is 3 time units. I cannot tell it as 3 seconds, 4 seconds, 5 seconds. It is 3 time units because it is dependent on that simulation tool, what you're using, your system, what you're using. Okay. So this is how you are providing the delays. So up to now, what you had done, you hadn't used this. You had written and A1 and the parameters. Now, along with this, you are specifying the delay. So that is what you are doing here. Okay. Any query